Okay, here is something that will mess with your head. You take one of the most powerful AI language models on the planet, a llama, a mistral, something that can write poetry and debug code. You ask it to understand a sentence, and what does it actually latch onto? The word the word and, a comma, a new line character, words that carry literally zero meaning.
Wait, you are saying these billion parameter models that can pass the bar exam are confused by articles.
Not confused exactly, more like haunted. There is this thing researchers do called a logit lens, where you take the model's internal representation of a sentence and project it back to see what words it is thinking about. And across multiple models, multiple architectures, the answer is almost always the most frequent, most meaningless tokens in the training data. It is a universal pattern.
Okay, but why does that actually matter? Like, if the model can still answer questions correctly, who cares what it is thinking internally?
It matters the moment you try to use these models for something called text embeddings, turning sentences into vectors, those lists of numbers that encode meaning. Embeddings are how you build search engines, recommendation systems, document clustering, semantic similarity tools. And if the model's internal representations are polluted by noise, your search results are garbage. You ask for heart disease research, and you get back results that are superficially similar in word frequency, not in actual meaning.
So this is a real production problem, not just a theoretical curiosity.
Massive production problem. There is a whole benchmark called MTEB, Massive Text Embedding Benchmark, and off-the-shelf LLMs consistently underperform on it compared to smaller models specifically trained for embeddings. Companies have been patching this with clever prompt engineering, like special templates or duplicating inputs, but those were band-aids. Nobody really understood why the problem existed.
Okay, so what did these researchers actually find? What is causing this?
So here is where it gets beautiful. Think about how LLMs are built. There is this matrix at the very end of the model, called the unembedding matrix, whose job is to convert the model's internal hidden state into a probability distribution over the entire vocabulary. It is basically the decoder, the thing that decides which word comes next. Everyone treats it as just an output layer and ignores it for everything else.
But it is not just an output layer.
It is not just an output layer. When you decompose it mathematically, using something called singular value decomposition, the same technique you would use in data compression, you get a spectrum of components. And the researchers discovered that the components at the extreme ends of that spectrum, what they call the edge spectrum, are specifically encoding high-frequency filler words. They are actively injecting the essence of the word the and the word and into every single embedding the model produces.
Okay, slow down. Singular value decomposition. Can you give me an intuition for what that actually means here? Because I am losing the thread.
Sure, imagine you have a giant mixing board, like a sound engineer's console with thousands of sliders. The unembedding matrix is that console. Singular value decomposition is like isolating which individual sliders are actually doing something important. The researchers found that the sliders at the very far left and far right of the board, the loudest and the quietest, are the ones cranking up the volume on meaningless filler words. The sliders in the middle are encoding actual semantics.
So the fix is just turn off the edge sliders.
Exactly. They call it embed filter. You take the embedding, project out the edge components, keep only the middle bulk of the spectrum, and suddenly your embeddings are actually about the meaning of the text. They ran the logit lens again after applying embed filter, and instead of the word the and the word and, you get words like activations, representations, language words that are actually in the input. The semantic signal was there the whole time, buried under static.
All right, I have to push back here. This sounds almost too clean. You are telling me that a single matrix operation, no retraining, just some linear algebra, fixes a fundamental flaw across multiple completely different model architectures.
I understand the skepticism, and honestly that was my first reaction too. But they tested it across QN, Llama, and Mistral, different sizes, different training runs, different companies, and the improvement held up every time, up to 14% better performance on MTEB. That consistency across architectures is actually strong evidence that they have identified something real about how LLMs work, not just a quirk of one model.
What about the ablation studies? Did they actually prove it is the edge spectrum doing the work, and not just the fact that they are reducing dimensions somehow?
This is exactly the right question, and they did test it. They tried randomly dropping dimensions, did not help. They tried just truncating the first half of dimensions, did not help, actually made things slightly worse. The specific removal of the edge spectrum is what matters. They even identified the theoretically optimal set of components to remove. An embed filter nearly matches that upper bound, which means it is close to the best possible version of this idea.
Okay, but there is a technique called whitening that also fixes anisotropy in embeddings, the same clustering problem you described. Why is this better than that?
Great catch, whitening does address a similar symptom. The key difference is that whitening requires a calibration dataset. You need real examples to compute the statistics and then apply the correction. Embed filter requires nothing external. It derives everything from the model's own weights. No data, no training, no calibration. You just need the model itself. And even head-to-head, embed filter outperforms whitening.
What are the actual limitations here? Because this all sounds very positive.
A few real ones. First, the method is described as primarily heuristic. They have intuitions for why it works. They have the mechanistic story, but the theoretical understanding is incomplete. They acknowledge they do not fully understand why the bulk spectrum specifically gives you more isotropic, better distributed embeddings. Second, the filtering ratio. How much of the edge you trim is a hyperparameter you have to tune per model, and for Mistral they needed an additional offset adjustment. It is not fully automatic.
And there is no fine-tuning or anything. So if you have a specialized domain like medical or legal text, does this still hold?
That is an open question. They tested on general MTEB tasks. The paper does not go deep on domain-specific performance. My intuition is it would still help. The filler word pollution problem is domain agnostic, but you would want to verify that experimentally before deploying it in, say, a clinical search system.
Okay, so let us talk about what this actually means practically. If I am building something with embeddings, what does this change for me?
Two things. First and most obviously, better search, better clustering, better similarity matching out of the box with models you already have with no retraining cost. You just apply this post-processing step. Second, and this one is genuinely surprising, you get dimensionality reduction for free. Because the transformation is mathematically distance-preserving, you can cut your embedding size by 4 or 8 times, and your similarity search still works just as well. That means your vector database is 8 times smaller, your retrieval is 8 times faster, your costs drop dramatically.
That second point is huge for anyone running embeddings at scale. You are talking about real infrastructure savings.
Billions of vectors at scale, yes. The storage and compute costs around embeddings are not trivial, and the fact that you get both quality improvement and efficiency improvement from the same operation, with no training overhead, is rare. Usually there is a trade-off.
What does this tell us more broadly about how LLMs work? Does this change how we should think about these models?
I think the deeper insight is that the unembedding matrix is not just a decoder. It is a lens into the model's semantic space. It encodes statistical structure about the training corpus in a way that is both a bug and potentially a feature. The fact that you can reverse engineer an average token from just the word frequency distribution and the model weights, that is a mechanistic interpretability result. It tells us something about how meaning is organized inside these models that was not understood before.
And there is a whole research program implied here. If the edge spectrum encodes frequency noise, what else is encoded in other parts of the spectrum? What is in the bulk that makes it semantically rich?
Exactly, they explicitly say they leave that to future work. And that is genuinely exciting. This is one of those papers where the finding itself is useful immediately, but the bigger contribution might be the conceptual framework it opens up. The unembedding matrix as a feature lens, that framing could lead to a whole new set of tools for understanding and improving LLMs.
All right, so the bottom line, what should someone take away from this?
If you use LLMs for text embeddings, there is a simple, free, training-free trick that makes them meaningfully better, and also smaller and faster. The tool is called Embed Filter. The code is on GitHub, and it works across Llama, Mistral, QWen, and likely every other similar architecture. Beyond the practical fix, buried inside every LLM is a hidden subspace that has been silently corrupting your embeddings this whole time, and now we know exactly where it lives.
And that's a wrap for today's episode. If you found this conversation valuable, consider subscribing and turning on notifications. We release new research breakdowns regularly, helping you stay on top of the latest discoveries without having to read every paper yourself. Thanks for listening, and we'll see you in the next one. Goodbye.